Your staple can only staple at the edges, run of the mill. Take a look at mine. A stapler that can rotate 360 degrees. Choose from 8 binding positions at will. Even the middle of a notebook can be easily bound. No more worries about not being able to staple the center seam with a stapler. Follow for more. Your staple.
Hello, good evening.
Good evening, ma'am.
Yeah. So, so this is a rescheduled class I could not take on Monday, and so today we are going to discuss about the assignment 9.
Yes,
Okay.
ma'am.
So did you solve it?
Yes, ma'am. I have submitted.
Yeah. So there is only 6 questions in this assignment. How did
Yeah.
it go?
Uh, Two are wrong. Four are correct.
Okay. Nice. Good try. Okay. So let's discuss then.
Yes, ma'am.
Okay, so the first question is in BeH2, two possible SALCs of hydrogen atom, one s orbital, psi1s A and psi1s B are this and this. So the correct statement among the following. So psi1 can form bonding as well as antibonding MOs with 2s. Psi2 can form bonding as well as antibonding with 2s. So first, so psi1s. So psi1s is this, so this is both positive combination, so it is plus and plus. Okay, so this is for hydrogen. Now for, if we, this is an SLC, linear combination of symmetry adapted linear combination. Okay, so for now, if beryllium, the bonding orbital will be 2s. So beryllium, we have, which has the symmetry of this, will be 2s orbital. Okay, so now beryllium 2s can be plus or it can be minus. Okay, so when it is the plus combination, this will form a bonding orbital. So this is bonding, and when it is, it will be this plus minus plus combination, so this will form the anti-bonding orbital. Okay, so this psi1 can form both bonding and anti-bonding orbital depending upon the phase of this beryllium 2s orbital. Okay, so the answer to this will be psi1 can form bonding as well as anti-bonding. Same goes for this also. Psi2 can also form bonding as well as anti-bonding with 2s. So if psi2 is, so psi2 is plus minus combination. So if no, psi2 cannot form because here if it is plus, this is neither bonding nor, same case goes with like this. So this is H, this is H, this is beryllium. This is bonding, this can be bonding interaction, but here it has anti-bonding interaction, so this will not form. Again, this is a anti-bonding interaction and this is a bonding interaction, so this also will not form. So only the plus combination will work with this beryllium 2s, and here it can form bonding as well as anti-bonding. So here only the first option is correct, not the second one. Psi1 can give non-bonding, Psi2 can give non-bonding. Okay, so this is not even non-bonding interactions. So these two are wrong. Okay, and here I have added this extra questions. So in the previous question, symmetry of Psi1 and Psi2 are. So what can be the symmetries of Psi1 and Psi2? Psi1 is phi1s plus phi1s, and Psi2 is phi1s minus phi1s. Okay, so can you tell, if you consider these two as the basis, what can be the symmetry? Can you guess?
Sigma bonding.
Ha, this is sigma, but tell me in terms of Millikan symbol. So this, okay, one H atom in plus phase, another H atom in plus phase. Okay, so this together we are considering this is a system. So what kind of point group it has? This is kind of linear diatomic molecule, right? So it
Yes,
belongs
ma'am.
to D infinity H.
Yes, ma'am.
Okay, so if you will consider this D infinity H, the elements will be C infinity E infinite times sigma V. There are many infinite number of elements. Okay, but if you will simply see from the character table of this combination, so the character, it will be E C infinity infinite times sigma V, infinite times sigma V, I infinite C2. Okay, so when you will operate E on this system, it will give you 2. Okay, because on operating this identity nothing will change, so plus remains plus and this plus also remains plus. On applying C infinity, this C infinity will be in this direction, right? In by any angle, the angle can be phi. So on plus on C infinity also nothing will change, so this is also the character will be 2. Sigma V will be also along sigma V will also along the principal axis, so it will be this plane at any angle, so this is also 2. When you will put I, this if it is atom A and if it is B, I will be here. Okay, so this will change place. So when there is a change of place, it won't contribute to the character and this will be 0. Similarly, C infinity, S infinity will be 0 and C2 is perpendicular. So if you will put C2 here or perpendicular, this 2 will change place. So this is also 0. So this is the reducible representation for this. Now we want to know that it consists of which irreducible representation. Okay, so if you will use that formula of great orthogonality theorem, we can, but we cannot use the formula actually, because that formula is equals to 1 by h something, some terms are there, 3 terms, but here h is infinity for this group, right? Order is infinity for this group. So we cannot, 1 by infinity will be 0, everything will come as 0. So we cannot use this formula here. So what we do it by inspection method. We can look at the character table of D infinity H. D infinity H, we can see the character table and we can figure out this plus plus combination belongs to, actually it belongs to the first totally symmetric representation, so it will be sigma g plus. Okay, and this plus minus combination, this is antisymmetric with respect to I only, so it is antisymmetric with respect to I. So this will belong to, instead of G, it will be U. Okay. Since it is antisymmetric, this thing will change to U. So this was our psi. This was psi1. Psi1 has sigma G plus and psi2 has sigma U plus. So how do we get this? We see the character table. So I don't have character table here. Let me get one. Well, for G infinity H. Okay, if we see this character table, the first row is the totally symmetric one. Okay,
Yes,
and
ma'am.
to which this plus plus combination belongs. If we'll put E on this, it will give 1. If we put C infinity, nothing will change. So sigma V, nothing will change. Character will be 1. If we put I, nothing will change. Now we are considering it as a single unit. Okay, now this is a linear combination. This is here what I did. Here we had two different atoms. So this was A, this is B. These were two different uh, atomic orbitals. Here these were atomic orbitals. Okay, two different atomic orbitals. That's why the character was 2, because the basis contains of two elements. Basis was two dimensional. This one was HA, one was HB. But here it is 1 1 only, because this is a set now. This is a linear combination. This whole thing is considered as 1. So basis here is one dimensional. Okay. So if we'll write its transformation with respect to E, it will be 1. With respect to C infinity, nothing will change. It will be 1, like that. Okay. You got my point?
Yes, ma'am.
Okay. So if we'll do it for all like written symmetry operations here, it will be all 1. So this will belong to totally symmetric representation. But for the antisymmetric one, this will under E it will be 1. Under C infinity it will be 1, because C infinity is in this direction. Under sigma V it will be 1, and under I only it will change. If we'll put I, this minus will come here, plus will go here. So under I, it will have negative character. Then this is S infinity. S infinity, S infinity, right? S infinity, how it is negative? Okay. So under S infinity also, so this is C infinity. First we'll put C infinity and then a perpendicular plane. So that perpendicular plane will be here. Okay, so that plane will change the plus and minus. So this also will be -1. Okay, and C2. C2 will also be perpendicular to the C infinity. So if this is C infinity, a C2 can be like this, perpendicular to this. So anything perpendicular to C infinity will change the positive and negative. So if this is, sorry, C2, this also will be -1. So this belongs to this combination 1, 1, 1, -1, -1, -1. The second one, the negative linear combination, this belongs to sigma U plus, which is the psi2. Okay, so this was an additional question. So here we can write the symmetries of the symmetries of psi1 and psi2 is sigma g plus and sigma u plus. Okay. Okay. So the next question is, the localized MO picture of methane is not tenable because carbon does not have atomic orbitals at 109.5 degree. LCAO with matching symmetry for hybrid orbitals cannot be formed. All four bonds of methane have different bond lengths, and tetrahedral character table does not have a four-dimensional representation. Okay, so it is saying that why we cannot use the localized MO picture. Localized MO picture means that the bond, the atomic orbitals which contribute to one bond are fixed. Okay, so but the delocalized MO picture is that the electron density, so the atomic orbitals forming all the bonds, there is a equal contribution. So the electron density is like equally, it is contributing to all the bonds. That is delocalized MO picture. So localized MO picture will say that there will be bond lengths of three bond lengths same and one different if we use the localized MO picture. But it is not the case. Actually, methane have all the four bond lengths same. So this localized MO theory does not hold because first of all, the carbon does not have atomic orbitals. So if this is carbon, what atomic orbitals it has? 1s, 2s, 2p. So if we have to make CH4, these atomic orbitals, so the bond angle is in CH4, the bond angle is 109.5 degrees. But these atomic orbital, one is spherical. So one is spherical, so it will be something like this, and the p orbitals will be, suppose this is 1p, this is another, and this is another. So these are the p orbitals. In none of them are at 109.5 degrees to each other. Okay, all the p orbitals are at 90 degrees, and this is spherically symmetric. Okay, so directly carbon atom cannot form the bond as it is. Okay, so the localized MO picture, first statement is true, that the atomic orbitals are not at correct orientation or direction, so they cannot form a localized bond. So first is correct. Okay, next is, in the tetrahedral character table there is no four-dimensional representation. D option is correct. Okay, so let me explain why. If we have tetrahedral character table, okay, so can you see we have this tetrahedral character table here. The dimensionality is maximum 3, which means it is saying that maximum degeneracy can be 3 only. But here we have 4 degenerate bonds. So if we have to write it, we have to write it in linear combination of these two. So actually it goes like A1 plus T2. So T2 is 3, A1 is 1, 1 plus 3 is equals to 4, which gives 4 bonds. But this linear combination does not mean that 3 bonds are of same type and 1 bond is different. This is what is described by delocalized MO picture. But localized MO picture would have said that one is same and other 3 are different. Okay. So we cannot take this. This option is also correct because there is directly there is no, so there could be one more here which would have been 4 something something. So there is no such irreducible, no such representation like this in the tetrahedral point group character table. So we cannot have directly localized MO picture of methane. Okay.
Yes, ma'am.
Are you getting what I'm telling?
Yeah.
Okay. Have you watched the lectures for this week, 9th week?
Yes, ma'am.
Yes, then you must be getting. Otherwise, it is very confusing
Yeah.
today. Okay. Yeah, so this question again is the same thing which I wrote here, A1 plus T2. So it is asking the LCAOs of 4 atoms in methane have the following symmetries. So how this has been solved? This has been solved in class, like, so the 4 symmetry. So we have to consider these S or hydrogen atom, pendant atom. So this is H. Let me write A, B, C and D. Okay, not considering the carbon here because linear combinations are created using the side atoms, not the central atom. So here we have these combinations. Now this can be in the positive phase. So which orbital for hydrogen? 1s, because there is only uh, one orbital available for bonding here. So 1s for all. Okay. So if the 1s is in positive phase, we will donate it denoted by this. So positive. If it is negative, we will denote it by like this. Now, since this is the tetrahedral geometry, so let me draw this here. It will not be a good. Okay. Let me see if we have. Okay. So this is a cube. How the 1s orbitals will be arranged here at alternate opposite corners. So if this is 1, here nothing will be there, here 1 will be there. Okay. Now down there nothing will be there, here it will be 1 and here it will be 1. So this forms a tetrahedral bond, which means now I have drawn this filled circles, which means it is in positive phase. So this psi1 is positive phase. So 1sa plus 1sb plus 1sc plus 1sd, all are in positive phase. Next possibility is that 2 will be in positive phase, 2 will be in So the next possibility can be these two is positive, here it is negative. So this can be 1sa plus 1sb minus 1sc, sorry, this will be minus 1st. Okay, so we will keep this one fixed and change these three. So again psi3 will be, this is fixed, 1sa minus 1sb plus 1sc minus 1st, and there will be one more combination, 1sa minus 1sb minus 1sc plus 1st. Okay, now when we will use the character table, we can see that this is totally symmetric. Character from character table of TD group, okay, which I have shown here, this character table. So when we use this one, we can see this phi 1, it will be totally symmetric, and it will belong to A1. Okay, A1 representation, the totally
Yes,
symmetric representation. Okay, and when you will, these all three, these will jointly belong to T2 representation. 3 0 minus 1 minus 1 1. T means triply degenerate. Okay, so all of them will belong to T2. So this belongs to T2. You can check. Suppose we'll take this one. Under E it will be same. So under E it will be 1. Under, what is next? C3. Under C3 it will be, if we'll apply C3, suppose this is the molecule. If you will apply C3, fix this, all three will change. So under C3 it will be 1. Under C2 it will be here, C2. So suppose if you're C2, it will be 2. No, actually we cannot take them as separate. This whole thing is a unit. This whole thing we have to take. So under E it will be 1. Nothing will happen. Under C3 these will change places, so it will become 0. And under C2 also it will change place, so it will be 0, not same. Next is S4 and sigma D. So S4 it will change places, so it should be 0, sigma D. Sir actually did not do it this way. What he did was, so he told like T2 is triply degenerate and we have 3 C2s. In the character table, we triply degenerate. T2 is triply degenerate, and we have 3 C2s, so they should be symmetric with respect to 3 C2s. So that's why T2 comes. Actually, it's a bit difficult how it is. It could have been T1 also. Sigma T. But do you have any idea why this is not T1 but T2?
No, ma'am.
Because T1 is also triply degenerate and the character of C2 is same in both T1 and T2, right? -1, -1. Only these two differ. So let's see. If we put S4, everything will change place. So it should be anti-symmetric with respect to S4. And with respect to sigma D, sigma D means along 2 bond. 2 will change places. I'm not clear about sigma D, but along sigma 4 it is anti-symmetric. Maybe that's why it's T2. Uh, okay. Okay, let's take it as it is. So it is T2. I'm not very sure why this is not T1. And also then these are the symmetry of SALCs. So symmetry of SALCs is A1 plus T2. So now these are 4 hydrogen atom done. Now there will be overlap. Next step is overlap with carbon atomic orbital. So carbon 2s, this belongs to A1 symmetry, and carbon 2p XYZ, this actually also belongs to T2 symmetry. So there should be matching symmetry, overlap between the SALCs and the atomic orbital of matching symmetry. So there will be psi 1 and 2s will overlap plus minus, and here 2pxyz will have linear combination with psi 2, psi 3 and psi 4. This will have psi 2, psi 3 and psi 4. Linear combination means both plus and minus combination. So it will generate total from here 2, from here 3 into 2, 6. So total 8 molecular orbitals, out of which 4 will be bonding, 4 will be antibonding, antibonding molecular orbital. Okay, so here the answer will be T2, not T1. A1 plus T2. This is the correct answer, not this. Not sure why T1 is not the answer. Okay. Okay, so for which question went wrong for you?
4 and 5.
4 and 5. Okay. So let's discuss 4. 4, okay. So for trigonal bipyramidal, so let's draw trigonal bipyramidal. Okay, now the equatorial bond involve orbitals of symmetry. So we have to consider the equatorial bond. Let's say this is sigma 1, sigma 2, sigma 3. I'm writing sigma because they want the symmetry of orbitals. Okay, so
Okay.
sigma 1 orbital, sigma 2, sigma 3. Let's name them sigma 4, sigma 5. Okay, now here our basis set is equatorial bonds, right? Equibonds,
Yes.
which means the basis set is orbital sigma 1, sigma 2, sigma 3, three-dimensional basis. And here the point group is, what is the point group of this?
D3H.
Yes, the point group is D3H, and order will be 12. You can sum this 1 plus 2 plus 3,
Yes, 12.
6, and then 6 here. So order is 12. Now we need to figure out that to which symmetry species out of these sigma 1, sigma 2 and sigma 3 jointly, it belongs to which symmetry species. So let's do that. So this is my sigma 1, sigma 2, sigma 3. Okay, here in between A is there. And we have, so let me write the, we need to find the tau equatorial. First is E, C3, 3C2. I'm writing the symmetry operations in D3H point group, which
Yeah.
is from here, from the character table.
Yeah.
2S3 and 3 sigma V. Now, if you will apply E on this, notice that I have not written here sigma 4 and sigma 5 because they are not in the basis. That doesn't count what happens to them.
Okay.
Okay. Now, under E, nothing will change. So, sigma 1 remains sigma 1, sigma 2 remains sigma 2, sigma 3 remains sigma 3. So, we have number of unchanged atom is 3.
3.
Here, we have to consider all of them as separate quantity because the question is asking the equatorial bonds. So, this is one quantity, this is one quantity, this is another quantity. So, it is not a linear combination. Now under E it is 3. When we'll apply C3, so if C3 will be from top, right, from here. If we'll apply C3, all three will change places.
Yeah.
So number of unshifted
0.
atom is 0. Or applying C2, C2 will be along the bond. This is C3. C2 will be like this, along. So if we are
1.
applying C2, only one will remain unshifted. Okay, so this is 1. Actually, we have to consider A also here. No, if we consider A, it is 1. Fine. Then sigma H,
3.
3. Then CS3,
0.
0. Sigma V,
1.
1. Fine. Now we need to find the contribution of irreducible representation into this reducible representation. So how do we do that? Using that formula, AI is equals to 1 by H summation R chi R chi IR. Okay. H is, so first what we have first, A1 dash, first irreducible representation A1 dash. So let me write contribution of A1 dash to this will be, order is 12, 1 upon 12. So this is 0, I am not writing it. This is also 0, I am not writing it. So the we will only have 4 terms, 1, 2, 3 and 4. Okay. Okay.
Okay.
Okay, because even if I multiply anything with 0, it will be 0. So I'm better
Yeah.
not to write that down. So
Sure.
yes. So 1 into 3, 1 because the coefficient is 1 into 3 and the character under A1 is 1. Here all the characters are 1. It is totally symmetric. So I will simply write 1, 1, 1, 1 for each.
Okay.
Next C3, C2. This I am not writing. So it is 3 into 1 into 1. Next this 1 into 3 into 1. This is 0. This is 3 into 1 into 1. So we have 3, 3, 3, 3. 12 by 12 equals to 1. Right?
Yes.
Next we have contribution of A2 dash. So 1 by 12, 1 into 3 into 1. So for A2 dash, where is the change? For C2 there is negative and sigma V there is negative. All others are 1.
Yes.
So let's write C3 I am not writing. For C2 it is 3 into 1 into 1 plus sigma H, it is negative. Sigma, I did some mistake. So C2 it is minus 1. This is minus 1. Okay. So this is E, this is C2. Now sigma H will be 3 into 1 into 1. S3 is 0. No need to write this. Then sigma V is minus 1. So we will have 3 into 1 into minus 1. So we have 3, 3, minus 3, minus 3. So it is 0.
0.
Yeah. So similarly, if you will do, we will get A E dash equal to 1 here, and A of the A1 double dash will be 0, and coefficient of A2 double dash will also be 0, and then lastly coefficient of E double dash will also be equal to 0. So these three and this is 0, and we have 1 contribution for A1 dash and E dash. So what was our basis? Equatorial bonds, right? So here this gamma equatorial, which was reducible, has contributions from A1 dash plus E dash. Okay.
Okay.
So here the answer will be A1 dash plus E dash. Oh, answer is not given actually. So it should be A1 dash E dash, and then the correct answer will be this. So what did you mark in your assignment? Which option?
I think first one was.
You marked first one. So answer is option. Actually, answer given is option A, which is okay, but here it should be dash. Dash is missing in the printing error it is. So our answer is not A1 plus E. Answer is A1 dash plus E dash. Dash because of the Mulligan symbol.
Okay.
Okay, so this is the fourth question. Okay. Now the next fifth question is for C2H4. C2H4 is what?
Ethane.
Yes. So it will be this. So let me write it. Sigma 1, sigma 2, sigma 3, sigma 4. A projection operator operates on sigma 2 to yield sigma 1 plus sigma 2 minus sigma 3 minus sigma 4. So the projection operator is of symmetry which? So the question is asking what is the symmetry of the projection operator. Okay. So let's reduce this. Here we have C2. This is C2Z. And X is in this direction, Y is in this direction. So the point group is D2H. Okay.
Yeah. This one.
So when you will, let's see the tau SALC first. Under E, the character will be 4 because all these 4 atomic orbitals, they will nothing will happen to them. Under E, it will be 4. Under C2Z, C2 is like this, coming out of this plane of the screen. So under C2Z, what will be the character? So when you will apply C2Z here, what will happen? So if this is C2Z, this will come here, this will come there. So the character will be
0.
0. Yes, everything will change place. So it will be 0. Then C2X. C2X will be in this direction.
Maybe
Again,
0.
again 0. Then C2Y.
0.
Yes. Then we have C2XY identity.
Maybe
0.
0.
Because everything will change. Then sigma XY.
Expect them. Maybe 0.
No, sigma XY is this plane,
Molecular plane.
molecular plane.
Okay. 2 1. 4.
4. Then sigma XZ.
So maybe 0.
0. And then lastly sigma YZ.
Same 0.
0. So this is the reducible representation tau SALC. Not SALC. We can write something uh, tau C2H4, let's say. Okay. I'm not writing it SALC because I have considered these 4 atomic orbitals separately. If I have to write SALC, it means I'm considering whole thing as a one thing, as a linear combination.
Okay.
Okay, so now if this is the reducible term, again we need to change it to the linear combination of irreducible representations. Okay, using the same thing which we did in the previous question, that formula.
Yeah.
Okay, so this will give this. That's right. Now tau C2H4 will be equal to Ag plus B1G. If you want, you can just use that formula and check. Plus B3U. So these four irreducible representation will come. Four different symmetries.
Okay.
Okay. Now we have to find whether it is P3Ag on sigma 2 or it is P B1G or projection operator of Bu symmetry, or it is B3U on sigma 2. Which one will give me this combination? Sigma 1 plus sigma 2 minus sigma 3 minus sigma 4. Which one will give me this combination? This we need to figure out. Okay?
Okay.
Okay, so let me tell you the answer. Otherwise, you will have to do it 4 times to check. Actually, the correct method is we have to start with the all four of them and then see which one is matching. But actually, let me tell you the answer. Otherwise, it will be very lengthy explanation. So the correct answer is this one, B3. So how it is the correct one? See, here we have this character table. B3U is this last row.
Yeah.
This is B3U. Plus 1, minus 1, minus 1, plus 1, minus 1, plus 1, plus 1, minus 1. Okay, so I'm going to write the same characters from here. So we have B3U, E, C2Z, C2Y, C2X, I, sigma XY, sigma YZ, sigma XY, it is sigma XZ, sigma YZ. So the characters for these, I'm copying this from the character table. First is plus 1,
Okay.
second is minus 1, this is minus 1, this is 1, this is I is minus 1, this is 1, 1, 1. Fine.
Yeah.
Now we need to find what will happen to this sigma 2 when we will apply the projection operator. So we need to find B3U applied on sigma 2. Sigma 2 we have to check. Now first operation is identity.
Yeah.
If we'll apply identity, it will remain sigma 2. Okay? And the
Yeah.
character for identity is plus 1. So this is plus 1 into sigma 2. I will write here, this is for identity. Next, C2Z. Z is here, coming out of the screen. C2 will go at the place of C4. Isn't it?
Yeah.
Here we have C2Z, right? If we will, it is pointing towards you. Okay, C2Z. So if we'll apply C to Z, this will go there, this will go there. So it will be sigma 4. But the character for C to Z is -1. So we have to multiply -1 sigma 4. Next, C to Y. Y was in this direction. So C to Y will be like this. So sigma 2 will change with sigma 3. And the coefficient character is -1. So again, -1 into sigma 3. This was for C2Z. This is for C2Y. Next is C2X. Character is 1. So 1 multiplied with C2X is like this. So these two will get changed. Are you getting?
Yes, ma'am.
Okay. Sigma 2. Sorry, sigma 1. Sigma 2 will become sigma 1. Next is identity. Under identity, it is character is -1. So let's write -1 into what will happen? This 2 will get changed because identity is here. Center of inversion is here.
Yes.
So sigma 2 will become what?
Sigma 2, sigma 3.
No, this is inversion center.
Oh, sigma 4.
Yes. So sigma 2 will become sigma 4. This is for inversion. Now this one, sigma xy, the character is 1 into,
Well,
so
what is
xy
it?
plane. Xy, suppose
Same,
this
sigma 2.
is, so xy plane will be like this plane. So sigma 2 will become sigma
Sigma
1.
2. Okay.
Sigma 2 will become sigma 1 because this is the xy plane. Can you see? I have drawn it here. This kind of plane.
Okay.
Here, like this it will be. So
Sigma
sigma
1.
2 will become sigma 1. If you put a plane here, it will reflect these two, right?
Yeah.
Sigma 2 will become sigma 1. Next this one, sigma xz, character is 1. Oh, sorry, last one was xy, right? Sorry, my mistake, you were right. Sorry. Sigma xy is this molecular plane. Next will be sigma xz, which I told earlier. Okay?
Yeah.
Am I clear?
Yes, ma'am.
Next is again yz plane. So it will be this plane, like this. A plane like this. So it will be
Sigma 3.
sigma 3. Yz should be, character here should be -1. See the character table? Yes, sigma yz, the character is here -1.
Okay.
Okay, so here we have to multiply it with minus. Now you see, sigma 2 is plus, sigma 1 is all plus, sigma 4 and sigma 3 are minus. So
Yeah.
this gives that projection operator of P3U when applied on sigma 2, it gives sigma 1 plus sigma 2 minus sigma 3 minus sigma 4. Okay?
Okay.
2 times. So this coefficient does not matter. So the answer to this question was, which I told, is P3U because
Yeah.
of this. Now otherwise you will have to do it. So this was the last. You will have to do it, check it with AG, B1G and B2U.
Yeah.
If you will do that, you will get like AG, you will get the totally symmetric representation, all plus. Okay.
Yeah.
And for next is what, B1G. You will get sigma 1 minus sigma 2 plus sigma 3 minus sigma 4. For B1G, you will get this. And the third is B2U. So B2U, you will get, so what we are doing, we are changing the sign. So
Yes, ma'am.
this will be sigma 1 minus sigma 2 minus sigma 3 plus sigma 4. Like this you will get something.
Why we have used the sigma 2 projection operator?
No, you can choose any other because all four are equivalent.
Okay.
Yeah, you can choose sigma 3 also, you will get the same answer.
Okay.
Yeah. But here the question says that it
Ah,
operates
sigma
on
2.
sigma 2, that's why I have chosen sigma 2.
Okay.
But
Okay.
since it is symmetric, all are same orbital,
Mm-hmm.
you will get the same answer with sigma 1 also, sigma 4 also, and sigma 3 also.
Sure, sure.
So you might have remembered this in class, I think. So I took sigma 1
Okay. Yes,
first.
ma'am.
Okay. Next is what? Huh. So the next question is, the delocalized MO picture of methane is in agreement with photoelectron spectroscopy and rotational Raman spectroscopy. So the correct answer is first one.
Raman and rotational Raman.
Yes. So the correct
Both.
answer is this, because the
Okay.
delocalized MO picture is the actual picture. So it gives three like A1 plus T2. This is 1, sigma 1, and sigma 2, sigma 3, sigma 4, and these are all bonding, so these are all filled, but it does not mean that sigma 1 is one bond and these are others. So these are molecular orbital, means it is delocalized over all the four bonds. So sigma 1 has contribution from all the four bonds, sigma 2 also has contribution from all the four bonds, and so on. So all the four bonds are equivalent.
Yes, ma'am.
Bond lengths are equivalent.
Yeah.
So the correct option is A here.
Yes, ma'am.
Yeah. Okay. So this was the last question for today's assignment. If you have any other doubts, you can ask.
No, ma'am.
So what was the second question that went wrong for you?
Mm,
You don't.
4 and 5.
Oh, 5 is this one.
Yeah. D3.
Okay. Okay. Now you got it now. You try to do it
Yes.
with other three also.
Yeah,
These
sure, ma'am.
these three also you try.
Yeah.
What you are getting, whether you are getting this thing or the any other thing, you let me know.
Sure, ma'am. I will try.
Yeah. Okay.
Okay, ma'am. Thank you.
Yeah. Okay, fine. I'll end the session then.